அண்டர்ஸ்டாண்ட் பண்ணி என்னமோ செஞ்சுட்டு இருந்திருக்காரு. யூஸ் பண்றதுக்கு.
Hello, good evening, everyone. So I thought we will look at the equilibrium part, the tutorial there, parts that we are continue to discussing. That is chemical equilibrium tutorial, the blue one, right? And we have discussed up to question number 57, right at the middle, page number 11. We are now moving to the page number 12. All right. Everybody okay with that? So I hope you found that place. Question number 58. Right? 58. Let's read that. Consider the following chemical reaction at the equilibrium state. A, B, B, C, C, D, D. Derive the relationship between Kp and Kc for this equilibrium. Simple A, capital A gas, right? Simple B, capital B gas. At equilibrium, simple C, capital C gas, and simple D, capital D gas. Can I ask you to look at the theory and remind you? Or you can say this way also, Kp is equal to partial pressure of C gas, right? Partial pressure of D gas divided by partial pressure of A gas. Don't worry about the stoichiometry. I will write that later. Partial pressure of A gas, partial pressure of B gas. And they should be powered to their stoichiometry, C, D, and simple A, simple B. That's how you get that. And Kc means, again, the same thing, concentration of C gas, concentration of D gas, divide by concentration of A gas and concentration of B gas. Powered to their stoichiometric coefficients, C, D, A, and B. And then what you do is you apply PV and RT. P is equal to CRT. So here Kp is equal to, concentration of C to the power C, RT to the power C. Concentration of D to the power D, RT to the power D. Divide by concentration of A to the power A, RT to the power A. Concentration of B to the power B, RT to the power B. So that means this part means it is Kc. So you know Kp is equal to Kc RT delta N. Delta N means summation of the stoichiometries of the products minus summation of the stoichiometries of the reactants. This is just the summary. Detailed derivation, I think I have given in the note, right? Consider, but let us work on the calculations. That's a difficult part. Consider the following equilibrium: QR3 gas, and then R2 gas, and QR5. QR5. 5 moles of QR3. 5 moles. Always work with the rise chart, right? 5 moles of QR3 and 3 moles of R2. 3 moles of R2, QR5 was kept in a closed container. 30% from the starting amount of QR3 has reacted. 30% means how much is that? 5 times 3, 15, 1.5%, 1.5 moles, right? So 1.5 moles has reacted. So 1 is to 1. Here also 1.5 moles has reacted. And then here you get plus 1.5 moles. And 5 minus 1.5 is 3.5. Tell me whether I am making any mistakes here. This is 1.5 moles. And this is also 1.5 moles. So if you want, you can write down that R reaction, I initial change, and the end equilibrium. Yeah. And pressure was 10.13, 10 to the power 5 pascals, Newton per square meters. Let me correct that. Newton per square meters. Calculate the Kp. 3.5 and 1.5 is equal to 5, 6.5. So molar fractions are 35 divided by 65. This is 15 divided by 65. And this is also 15 divided by 65. Is it clear? And the partial pressures, like, we will look at partial pressures multiplied by P, multiplied by P, multiplied by P. Are you're okay with this number of moles? And then they ask you to calculate Kp. Kp is equal to partial pressure of QR5 gas. Divide by what? Partial pressure of QR3. QR3 gas and partial pressure of R2. Partial pressure of R2 gas. So what are those numbers? QR5 is 15 divided by 65 pressure. This is also 35P divided by 65 pressure. 65 pressure plus 15 divided by 65 pressure. So you can see that it will cancel out, right? This will cancel out. And that gives you 65 divided by 35. Pressure is equal to 10.13, 10 to the power 5 pascals. Is it clear? What is the answer that you get? Now somebody tell me the answer. 35 times 10.13, 10 to the power 5. What did you get? 1.83, 10 to the power minus 6. 10 to the power minus 6 pascals. Is it clear? Right. Good. Good. Very good. I will also write down this one so that next time I can give the answers also. Pascal, right? Everybody okay? Na? Right. Good. So I hope you are all okay. Right. Let's see whether, what do you say? 1.2 kila දෙන්නේ නැහැ. 1.83 කියලා තමයි එන්නේ. Right. Okay. Right. Question number 59. Let's do that. 59. Kc for the following equilibrium at a certain temperature is 25. Assume that the reaction was started with the same number of moles of hydrogen and iodine. Illustrate graphically how the concentration of hydrogen and iodine of this reaction change with the time as the temperature. Right. Change with the time at the same temperature. Right. I was looking at this. Hydrogen, hydrogen gas, let's say iodine gas, and it gives you HI, 2HI. So since it doesn't say how many moles, we will take it as n number of moles. Let me change the color. N number of moles, here also n number of moles, because you use the same number of moles, isn't it? And let us say X has reacted. This is also X, and this will give you 2X. So now at equilibrium, n minus X divided by volume. What does it say? Kc, right? N minus X divided by volume. That is the concentration. So 2X divided by volume. That is also the concentration. Now, what do you do? What is the next thing that you do? You use the Kc and do the calculation. Kc is equal to, what is that? Hydrogen iodide squared. Divide by hydrogen gas concentration, and then what else? Iodine gas concentration. What is that, Puta? 25 is equal to 2x divided by volume squared. Divide by n minus x divided by v, n minus x divided b, that is also squared. And you can see this volume and volume cancels out. And then what you do, you take the square root on both sides. 5. 5 is equal to 2x divided by n minus x. What do you get? 5n minus 5x is equal to 2x. 7x is equal to 5n. So therefore, x is equal to 5n divided by 7. This is the This is the number of moles. 5 divided by 7, I'd like to take it as a decimal and see how this is. 0.714 it says. What do you think? 714N. So this is the amount that has reacted. X is the amount that has reacted. What they want is hydrogen and iodine change in the concentration. What is the hydrogen concentration? Hydrogen concentration is equal to, you started with N moles. 0.714N has reacted. So what is the number? 0.714. 1 minus 0.714. You get 0.286. 0.286 N. Please double check. Tell me whether I have done any mistakes. Hydrogen iodide, what is the amount? Hydrogen iodide is 2.714 multiplied by 2 because it is 2x here. Look at the laser pointer window. Here, 2x, right? We don't know the volume, doesn't matter. Hydrogen iodide is equal to 2 times this value, 1.428 N. So what do they say? They say, how does the concentration vary? So how does the concentration vary? It will be like this. This is the time. Let us say it take this time to reach equilibrium, right? And this is 0. Let us say this is 0.5, 0.25. And this is 0.5. This is 0.75. This is 1. And then 1.25. I might not have enough space there. Let's say, let's extend it a little bit further. And this will be 1.5. And this is N divided by V. Whatever the number times N divided by V. So you start with hydrogen iodide. How many moles? You start with N number of moles. So this is hydrogen. And at the equilibrium, it reduced to 0.286. 2.5286 is slightly higher. Did you understand that? Right. Okay. Now I'll use a different color to do the next one. Hydrogen iodide, you start with this value. And then 1.428. 428. 1.5, slightly lower. Not 1.5. 1.428. So what would happen? It will go like that. And then it becomes a constant. So that is hydrogen iodide. And then what is the other one? Other one is 0.286. 0.286, it should vary like this. And it should maintain constant throughout. So this will be, what is that? Hydrogen iodide. This is hydrogen. Yes. Did you understand that if somebody asks you how does the variation of iodine take place, iodine also maps the same point like this, just like that, right? Right? And it changes in the same line. Yeah. Okay. But then I understood, I can't get that properly. Yeah, right there. Like that. Huh? Everybody okay? This is the purple color one is iodine. But they don't ask iodine. Did you understand that, Putala? You all got the answer, right? Did you? Okay, right, good. Right. So likewise, you can work out that, that is after equilibrium, after reaching that equilibrium. Right. Very good. Let's look at the question. 0.2 moles of NO, 0.1 moles of hydrogen to kept in the beginning of the container this much. Following equilibrium occur. Right, okay. So we will summarize this. So first of all, let us note down the reaction. 2 NO gas plus 2 hydrogen gas. At equilibrium, you get nitrogen gas. And then 2H2O. That is also in the gas phase, right? 0.2 moles of NO. So 0.2 moles of NO is there. 0.1 moles of hydrogen. 0.1 moles of hydrogen is there. 0.2 moles of water. 0.2 moles of water is there, right? So this is the initial amount. Was kept at the beginning of the container with a volume 0.02. The volume is 0.02. Following equilibrium occur at temperature 500 Kelvin, you will have 500 Kelvin, the reaction take place in the forward direction, right? 0.15 moles of NO was remained in the system. 0.15 to remain out of 0.2, 0.05 has reacted, isn't it? 0.05 has reacted so that you have 0.15. Did I do it right? Is it clear? So stoichiometry is 2:2. So here also you need to see 0.05 reacting. So that means you have 0.05 remaining. Here 2:1. 2:1, right? 2:1 means you get 0.025. So that means here you have 0.025 moles. Here you add 0.05 is 2:2. So there you get 0.25 moles, right? And if you look at the concentration, you divide it by volume, divide it by volume, divide it by volume, divide it by volume, right? Whatever the concentration that you get, whatever the volume that you get. Is it clear? Right, okay. So what do they ask? They ask you to calculate the Kc for the reaction. So how do you calculate the Kc? Kc is equal to substitution nitrogen, physical state, hydrogen, no, water, physical state squared, divide by, what is the other one? NO, gas, physical state squared, and hydrogen, gas, and squared. So you write down that. Nitrogen. Nitrogen is 0.025 divided by volume times next one is 0.25, right? Divide by volume squared. This is divided by, what is this? 0.15 divided by volume squared multiplied by, this is 0.05 divided by volume squared. What is the unit? Moles per cubic meter. 2 plus 1 is 3 minus 4. 3 minus 4. Right. Okay. So our unit is cubic meters per mole. Right. Let's simplify that. How do you simplify this? Volume squared cancels out. Volume, and there is only one volume that is remaining. I will write it as V and then cut off this. So our answer is 0.025 times 0.25 squared. Volume 1 over V. So you have to get that to the top. Our value is 0.02. Divide by, this one is 0.15 squared times 0.05 squared. Right, let me do the calculation and see. 0.25 squared multiplied by 0.02 multiplied by 0.025. Okay? Divide by 0.15 squared. Divide by 0.05 also scared. Now I am scared to say this. 0.55. 555. Is that the answer? Cubic meters per mole. Is that what you get? Okay. Right. Good. And now then others say that they got the answer and then somebody else says 11.1. Can you double check? Right? Somebody else also can someone confirm the answer so that we can move on? Not done. Did you divide it by 0.02 and multiply actually? (11.1) times 0.02. Okay. So we'll take that answer, this answer, right? And then they say calculate the Kp for this equilibrium. You know Kp is equal to Kp Kc RT delta N. RT delta N, what is the delta N? 2 plus 1 is 3, 3 minus 4, that is minus 1. So what is Kc? Kc is equal to Kp divided by RT multiplied by RT. What do they ask? They Kp, yeah, okay. Kp. Right. We use that same equation, nah? Right. So Kp is equal to Kc divided by RT. Kc is 0.55 cubic meters per mole. RT is 8.314 joules per moles per Kelvin. Temperature 500 Kelvin. What is the value? 0.55 divided by 8.314 times 500. What is the answer? 1.32, 10 to the power minus 4. Per Pascal. Did you all get that? Hmm? Yeah, okay. So there's one person confirming the answer, but then others, did you all do? So we'll settle for that, huh? Then. So let me write that 0.55 and the other one. Yes, there's some more confirmation, right? Okay, thank you. So 1.32, 10 to the power minus 4. Right. So the 59 is done. Now let us look at question number 60. 60 looks like a kind of a longer question, isn't it? But let us gradually understand and try to work that out. Following equilibrium can be observed in the vapor phase at the temperatures above 100 degrees. So you have A gas plus B gas at equilibrium, P gas, and then Q gas. A gas bulb was filled with equimolar gaseous mixture that contains only A and B. So here you have N here you have N here. The bulb and its content was heated to 200 degrees Celsius. 200 degrees Celsius. Right. Experiment 1. So I will say experiment 1. Right. It was found that the molar fraction of P inside the bulb after equilibrium is reached is 0.2. Then make a equilibrium me a 0.2. Right? So this is 0.2, molar fraction is 0.2. After that, bulb and its content was heated to 400 degrees. Molar fraction of XA of that equilibrium mixture was 0.2. So let me take the same sample and then we will keep it here. This is experiment 2. Temperature is 400 degrees, 400, and something is 0.2. What is that? Molar fraction of A is 0.2. So this is what you have. The mixture was 0.2. Calculate the equilibrium molar fractions of BAQ at 10 to 100 degrees. Now the easiest way to do is, this is P, and P to Q ratio is 1:1. So if the number of moles are the same, molar fractions are also the same. 0.2, 0.2. And these number of moles are also the same. Right? So if you have 0.2, 0.2 here, P and Q, 0.2, 0.2, that is total molar fraction is 0.4. Did you understand? The 0.2, 0.2 total molar fraction is 0.4. And the remaining molar fractions is equally divided between A and B because you start with the same number of moles. So 0.6, that means this should be 0.3 and 0.3. Now check whether you understood that part. P is 0.2. Therefore, Q also should be 0.2. Why is that? Stoichiometry is 1:2, 1:1. So P and Q is 0.4. The remainder is A and B. It should be equally divided. 0.3, 0.3 molar fractions. Did you understand that? Right. So keeping that also in mind, can you tell me how you can work on the 400 degrees? If this is 0.2, this should be also 0.2. Why? Because A and B you started with the equal number of moles and they should be divided equally. So 0.2, 0.2 altogether 0.4. 0.4, that means this one should have 0.6. How do you have 0.6? Equally divided, 0.3 and 0.3. And equally divided. Is it clear? Did you understand that? Calculate the equilibrium molar fractions of 200 degrees. Did you understand that? Any questions, Puta? Right, okay. Any questions? If there's any question, anything to ask, you need to ask that. All right? Right, okay. Calculate the Kp for the equilibrium. Kp is equal to, what is that? Partial pressure of P times partial pressure of Q divided by partial pressure of A times partial pressure of B. So what is that? Molar fraction, 0.2 total pressure. We don't know the total pressure. 0.2 total pressure. Divide by 0.3 total pressure multiplied by 0.3 total pressure. Did you understand that? So pressure, 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 all pressures cancels out. Right? So 0.2 times 0.2 is 4. 4 divided by 9. I didn't understand that better. How do you equal to 1 mole? Not 1 mole. Summation of molar fractions is equal to 1 in a mixture. Not 1 moles. This is the molar fraction. When you add all the molar fractions in a sample mixture, it should be equal to 1 mole. Did you understand that? These two are equal and these two are separately equal. You need to tell me. Check whether you understood that. The person who posed the question. 4 divided by 9. Right. Calculate the equilibrium molar fractions of BPQ at 400. Now we have already calculated this. These are the molar fractions. Right? By giving reasons, derive the sign of the enthalpy change of the forward reaction using above data and calculation. So what is this? You can see earlier it was 0.2, 0.2. Now it is 0.3, 0.3 when you heat. When you heat, forward reaction is favored. Right? Forward reaction is favored. Right? Forward reaction is favored. So it says derive the sign of the enthalpy change. Sign of the enthalpy change means it is when you heat it, forward reaction is favored means it should be endothermic. What is the sign? Delta H is positive. Oh, no, okay, right. You ask a question, but I'm not going to state what the question is, but instead I'll do this calculation. I'll look at this calculation little longer, right? How you get that. Let's say you copy it down here, paste it. Right. Now, Buddha, they say n number of moles, equal number of moles of A and B. Make a n. This is also n. Right. So let us say X reacted, and it gives you X here and X here. Right. So what is the number of moles? N minus X. N minus X. This is X. This is X. Right. What is the total number of moles? Total here. Total number of moles is N minus X plus N minus X plus X plus X. So this and this cancels out. This and this cancels out. Total number of moles is 2N. So what is the molar fraction? Molar fraction is N minus X divided by N. N minus X divided by N. This is X divided by N. This is also X divided by N. What there another? Right? So X divided by N is equal to, it says 2 divided by 10. 0.2 means that 2 divided by 10. So what is X? X is equal to 2 divided by 10 N. Again, 0.2 N. Now substitute. 0.2 N divided by N. That's 0.2 N. 0.2 N divided by N. 0.2 N. Right? Not 10 neither. It's 2N. Total number of moles 2N. 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 Put in there. This is 2N. So put a make a total number of moles. So I have taken it as N. It should be 2N. So what is that? X is equal to 4N divided by 10. How many? 4N divided by 10 is equal to 0.4N. So 0.4N divided by 2N is equal to 0.2. 0.4N divided by 2N is equal to 0.2. N minus 0.4N is equal to 0.6N divided by 2N is equal to 0.3. That is the same value that you get here also. So that is why these two are equally distributed and these two are equally distributed. Haridha, did you understand that? I think that is a kind of a lengthy way of doing it, where you get the same answer. Right, okay. So it's an endothermic process. Right, thank you. Right, no problem. Haridha, name the principle that can be used to predict the behavior of the equilibrium. What is the principle? Le Chatelier's principle. Right. The experiment one performed at 200 was performed with the same number of moles at the same temperature, but instead inside a container with a volume of half of the above bulb. What is the content of the equilibrium mixture? The maker, this one, has no effect on the pressure. When the volume is reduced, the pressure should change. But pressure is not a parameter. The Kp does not depend on the pressure here, right? It is in the same temperature. So we didn't do anything to this. Only thing is we reduce the volume to half of the value. So the equilibrium doesn't favor in the forward direction or the backward direction, and you get the same composition, right? So no change in the composition. Is it clear? Balan, right? You can ask questions as much as possible. You need to ask that, right? Without a doubt. Please do that. Is it clear, Putala? Did you understand that? That is question number 60. Everybody? Anything? Anything to ask? Now let us look at question number 61. Go to the next page. Question number 61. A glass container with a volume of 5 cubic decimeters. So this has a volume of 5 cubic decimeters. Filled with a gas named P that behaves ideally. Pressure inside this container is 1.995. 1.995. 10 to the power 5 pascals. P is dissociated at the temperature above 100, giving the following equilibrium. P dissociates above 100, giving this equilibrium. Q gas plus R gas. When the container that contains P at 27 degrees Celsius, so earlier it was 27 degrees Celsius, heated to 127 degrees Celsius. 127 degrees Celsius. You have now P, new equilibrium, P equilibrium. You get Q gas, also R gas. You got it? Right. The pressure inside the container is constant at 4.656. Weird numbers. 10 to the power 5 pascals. The volume of the container is unchanged upon heating. So no change. Whatever the volume that was there is the same volume here. 5 cubic decimeters. So this is also 5 cubic decimeters. 5 cubic decimeters. Content of the equilibrium. There's a question earlier. Content of the equilibrium mixture remains the same at constant temperatures and pressures regardless the changes made to the volume. If you make a change to the volume and if the pressure changes, then you might have either the forward reaction or the backward reaction because QP changes. No? So it might change the forward or the backward direction. So it might not. Now, if the pressure changes, the equilibrium get disturbed in certain reactions. Even if you have the temperature constant, it will give you the same equilibrium constant, but different amounts of the equilibrium. If it participates, if the pressure participates in the QP. But in this case, earlier case, QP doesn't depends on the pressure also. So there's no effect. Is it clear? I don't know whether I answered your question. That is what I understood from your typing there. Abhi, okay, yeah, okay, right, fine. So, right, okay. So you get this, yeah, calculate the nearest first decimal point, the total number of moles contains inside the container in the following, right? So let us apply PV and RT. I'll use a little bit of a brighter color here. Number of moles is equal PV divided by RT. Pressure 1.995, 10 to the power 5 pascals. Volume 5, 10 to the power minus 3 cubic decimeters, cubic meters. R 8.314 joules per moles per Kelvin. Temperature is 300. What is the value? Right? 1.995 10 to the power 5. 5 10 to the power minus 3 divided by 8.314 times 300. 8.314. 300. What did you get? 0.3999, let us say 0.4. 0.4 moles are there. If they said the reaction take place in a rigid container, then volume didn't change. No, it doesn't change. If it is a rigid container, the volume doesn't change. Man, right? No change in the volume. Right? Harneda, I hope I'm answering. I don't know. You're meaning something else and I'm answering something else. If they said reaction doesn't take place a rigid container, no volume, no change in the volume. Right. Okay. Right. So now what will happen is, now what is the next one? When the equilibrium is reached at 127 also, let us calculate the number of moles. Number of moles is equal PV divided by RT. Pressure is 4.656, 10 to the power 5 pascals. And then volume is 5 10 to the power minus 3 cubic meters. R is equal to 8.314 joules per moles per Kelvin. And the temperature is equal to 400 Kelvin. That will give you the number of moles. What is that? 10 to the power 2, double zero cancels out. 4.656 4.656 times 5 divided by 8.314 times 0.7. So that's 0.7. Right? Okay. Using the data above, calculate the equilibrium constant Kp for the above equilibrium. Right. So we will say P gas. Then at equilibrium, you get Q gas plus R gas. You started with 0.4. 0.4 minus X has reacted. X here, X here. So that means 0.4 plus X is equal to 0.7. X is equal to 0.3. 0.4 minus X cancels out X points. X is 0.3. So that means this is 0.1 here. This is 0.3 here. This is 0.3 here. What are the molar fractions? 1 over 7, 3 over 7, and 3 over 7. Partial pressures P, P, P. Haridhar. Equilibrium constant Kp is equal to, what is that? Partial pressure of Q. Are you all Looking at this, partial pressure of R divided by partial pressure of P. What are the numbers? 3 divided by 7P multiplied by 3 divided by 7P. 1 divided by 7P, right? 7 cancels out, P and P cancels out. 9 divided by 7. Total pressure is 4.656. 10 to the power 5 pascals. Clear? 9 times 4.656, 10 to the power 5 divided by 7. What is the answer you got? මට ආව අමුතු number එකක් 5.98 කියලා. 1 2 3 4 5. What is your answer? Very weird number. Same answer. Okay. Others, can somebody confirm? එකක් දෙකක් එන්න ඕනේ. එතකොට තමයි I also feel little okay. Right, same answer. Okay. Somebody says same answer. Others, they also got the same answer. Yeah. Same answer. All right. Good. Yeah. Good. Let me write that as well. Yeah. Okay. 5.98 10 to the power 5. 5.98 10 to the power 5 pascals. Right. Okay. Then an inert gas named Z was inserted into the container. Right? Inserted into the container. When the system reaches equilibrium again, the pressure inside the container is 6.651 10 to the power 5. 6.651 10 to the power 5 pascals. Calculate the molar fractions and the partial pressures of P, Q, R, Z under these conditions. Right. Molar fractions and partial pressures. You understand that this equilibrium partial pressure doesn't change. Because when you add inert gases, right? I have done the theory here. But I'll remind you, when you add an inert gas, total number of moles increases. So that the molar fraction will reduce. Molar fraction will reduce, but the total pressure increases. They cancel out each other. So these partial pressures should not change. No change in the partial pressures. Is it clear? Did you understand that? When you add an inert gas, no change in the partial pressures of these components. Because the total number of moles increases, molar fraction decreases. But because the total number of moles increases, total pressure increases. They exactly cancel out each other. Right? Is it clear? Then is that okay? So I'll write here, when an inert gas is added, total number of moles increases. Therefore, molar fraction decreases. Partial pressure, no change. Check whether you understood that. Clear. Okay. How about to increase pressure is the pressure of the inert gas. Yes, exactly. Increased pressure is the pressure of the inert gas. So what you have is calculate the molar fraction and the partial pressures of P, Q, R, Z under this one. So if you look at the partial pressure of P is the same pressure earlier. Right? 1 over 7P. 1 over 7 times pressure. What is the earlier pressure? 4.656. 4.656 10 to the power 5 pascals. That's okay, na? Right? 4.656 10 to the power 5 pascals divided by 7 is equal to 6.65. 10 to the power 1, 2, 3, 4. 4 pascals. Partial pressure of Q is equal to partial pressure of R is equal to 3 over 7, I think. Right? 3 over 7. Yes, 3 over 7 times 4.656. Don't sleep. Alright. 10 to the power 5. 3 times 4.656 10 to the power 5 divided by 7 is equal to 1.99 10 to the power 1, 2, 3, 4, 5. අපි කියමු 2 කියලා 2 10 to the power 5 pascals, right? So what is the partial pressure of Z? Partial pressure of Z is due to the increase in the pressure is due to the inert gas. So what was the pressure? 6.651. 6.651 minus earlier 4.656. In a very weird decimal places, ne? Partial pressure. I very much don't like this 656. Yeah, then 1.995 10 to the power 5 pascals. Clear? Now, what do they ask? They ask you to calculate the pressure inside this. Then the system reaches fraction and partial pressure. Molar fractions also they ask. So, molar fraction of P times the total pressure is equal to molar fraction, total pressure is equal to partial pressure of P. Molar fraction of P, total pressure is equal to the 6.651. 10 to the power 5 pascals is equal to partial pressure of P. Partial pressure of P is 6.65 10 to the power 4 pascals. So I'll take it as 1 over 10. Nah? 1 over 10. Clear? What is the partial pressure of Q? Molar fraction of Q. Molar fraction of Q is equal to 6.65 10 to 6.65. I mean, 2 10 to the power 2 10 to the power 5. 2 10 to the power 5 divide by 6.65 10 to the power 5. So what is that? 2 divided by 6.65. So equal to 0.3, 0.3. That is 3 divided by 10. So 3 divided by 10, x cube. XR is also the same thing. So if it is 336 plus 1 is 7, the other one is 3. X Z is also 3 divided by 10. Right? Something like that. Well, check whether you understood that. Dalton's law of partial pressures. Did you all get those answers? $61. Can you confirm those answers? Did you all do? Yes, sir. Okay, right. Right. How about you? Okay. Yes. Any others? Any others who has tried? Okay. Right. Fine. So, like just like that. I mean, if you're okay with that, anyway, I will send you the document so that if there are certain things missing, we can always write it down and correct those answers. Right? The next one is question number 62. That is the last question, last question in physical chemistry. So we'll look at that last question. When you correct and give the paper, I'm correcting. At the moment, I'm correcting. I have a lot of things these days on my plate. There were some other exams also. I'm correcting them as well. But I will try my best to give it to you on මේ මණ්ඩේවත් දෙන්න මම try කරන්න. කොහොම හරි ඉතින් කරන්න ඕනේ. Will do. හරි? Yeah, I'm correcting. Right. හරි. then එච්චර හිතන්න එපා. Right? Okay. Once the exam is done, okay, you're right. ගැන වැඩි ලකුණු ගැන හිතන්න එපා. වැඩි හිතන්න එපා. Just move on. ඔය shape එකේ අපි යනවා. හරි වෙයි කියලා යනවා. Right? shape එකේ යනවා. Alright, I'll correct it. Shall we do question number 62? Question number 62. This one, help me to do this. Steam reacts with carbon at high pressure and temperature above 450 degrees to produce an equimolar mixture, hydrogen and carbon monoxide known as the sign gas. It's called synthesis gas and synthesis. So it's called sign gas. The equilibrium reaction takes place in accordance with the following equation. Carbon solid plus H2O gas at equilibrium, carbon monoxide gas and hydrogen gas. A rigid vessel, volume is constant. There was an assumption, calculate the molar fraction, give any assumptions you use in these calculations. Assumptions earlier assumptions, what are the assumptions? Volume, no change in the volume. And inert gas also behaves as an ideal gas. Right? Sorry, I disturbed you. Sorry. Let's read it again. A rigid vessel whose volume remains constant at 5 cubic decimeters contains nitrogen gas, 0.843 grams powdered carbon, 5 cubic decimeters. Right? And then there's this powdered carbon here. What is the volume? 0.843 cubic decimeters of powdered carbon at a pressure 10 to the power 5. And temperature is 127. That means 400 Kelvin. 0.5 moles of steam is then introduced into this. Steam is then introduced into the vessel and the temperature of the vessel is increased to 527. Let's change this into 527. What is 527, 273, 57, 800 Kelvin? But I want to double check. 527, 273, okay, 800 Kelvin, right? So this reacts. At this temperature, only the above reaction takes place. When the equilibrium is attained, the pressure inside the vessel was found to be 13.2, 10 to the power 5 pascals. Once the equilibrium is attained. Assuming that the change in the volume of the carbon powder due to the reaction is negligible. So carbon reacts, the change is negligible, and stating any other assumptions you make, answer the following. Right. Calculate the number of moles of nitrogen gas present. We have nitrogen. Okay. Yeah. So there's nitrogen gas also. So let us look at the number of moles of nitrogen. Nitrogen PV is equal to nRT. PV divided by RT. So there's nitrogen as well. What is the pressure? Pressure is 10 to the power 5 pascals. Volume, what is the volume? 5 cubic decimeters, 5 minus the remaining ones, 0.5 minus 0.843 is equal to 4.157. 4.157 cubic decimeters, 10 to the power minus 3 cubic meters, right? Divide by 8.314 joules per moles per Kelvin. What is the temperature? What is the temperature? 400 Kelvin. So you can see 10 to the power minus 3, 10 to the power 2, double zeros cancels out. This and this cancels out. That is 2, I think. 1 divided by 8 is equal to 0.125. What do you think? Is that okay? Sure, nitrogen is present. Okay. Everybody okay with that? Nitrogen is present. Right. Everybody okay with that? Yeah, okay. See, now we'll go to the next one. In the next one, what you have is, you have a reaction. This equilibrium is there. Mama, I will write it down, that equilibrium. We will paste it and see. This reaction take place. This is a solid. So, what am I paddling? Yeah. So remember, this is a solid. And how many molecules of water did we add? We add something. 0.5 moles of water. We added it at the very beginning or later? Okay. 0.5 moles of water was added. Steam into vessel and the temperature 520. That is it. Okay, right. So X has reacted. This will give you X here. This will give you X here. There's no other reaction taking place. How does the volume become 4.157? Putha, now total volume is 5 cubic decimeters. The carbon volume is 0.843. So there you don't have nitrogen. The remaining volume. Volume. So they talk about this volume. Except this part. Is it clear? Because that's a solid. Right, okay. So there you have, right? So you get, now this one is 0.5 minus X. This is X as well. This is X as well. Oh, no, moles. What is that? After the equilibrium is attained, 526, calculate the total number of moles. We'll do that. Number of moles is equal PV divided by RT. Pressure is 13.2 10 to the power 5. Volume, what is the volume? What is the volume? We calculate 4.157. So it says no change in the volume, apparent change in the volume due to reaction with carbon. So this will give you Pascal, gives you cubic meters, megapascal, and this is cubic meters. R 8.314 joules per moles per Kelvin. 4 point, make a 2. 10 to the power minus 3, 10 to the power 2. Yeah, 13.2 divided by 16. 0.825. Is this the total number of moles? 0.825. Yeah, okay, right. 0.825. Right, okay. Then number of moles of each moles of hydrogen and carbon, steam, hydrogen and carbon. So now if you look at this one, you have 0.5 minus x. Then you have plus x. You have plus x. Then there was nitrogen also, how much? 0.125. Now don't forget nitrogen. It's there. How is it? 0.825. So minus x plus x cancels out. 0.625 plus x is equal to 0.825. X is equal to 0.2. 0.2. Did you understand that, Haridha? So what do they ask? They ask you to calculate number of moles of each of steam, hydrogen and carbon monoxide. Number of moles of carbon monoxide is equal to number of moles of hydrogen. These are equal to 0.2 moles. Number of moles of steam is equal to how much? 0.5 minus 0.2, 0.3 moles. Right? And then what else? 0.2, 0.3. It's number of moles. Partial pressures of these ones. Partial pressures. Right. Partial pressures of what? Carbon monoxide is equal to partial pressure of hydrogen. Is equal to 0.2 divided by 0.825 multiplied by total pressure 13.2. 10 to the power 5 pascals. 0.2 multiplied by 13.2, 10 to the power 5 divided by 0.825 is equal to 3.2. I like that answer. I put it round, like, it's a good number. 1, 2, 3, 4, 5. Is it clear? I'll do the calculation. You tell me the other one also. Partial pressure of water. What is the partial pressure of water? Partial pressure of water is 0.3 divided by 0.825 and multiplied by 13.2, 10 to the power 5 pascals. What do you get? Yes. Right. Okay. 0.3 times 13.2 divided by 0.825. 4.8. This is also 4.8, 10 to the power 5. So 3.2 plus 3.2 plus 4.8. That is 11.2. 11.2, 13.2 minus 11.2 is 2. The other one is partial pressure of nitrogen is you reduce it from the total pressure. 2 10 to the power 5. These are all past paper questions. Right, okay. Presenting. Right. Calculate the equilibrium constant Kp of the reaction. Kp of the reaction. What is the Kp? Kp is equal partial pressure of carbon monoxide gas times partial pressure of hydrogen gas divided by partial pressure of water. Partial pressure of water gas. So what are the values? Carbon monoxide and hydrogen are 3.2 10 to the power 5. 3.2 10 to the power 5 multiplied by 3.2 10 to the power 5. Divide by 2 10 to the power 5 pascals, right? 3.2 10 to the power 5 times 3.2 divided by 2 is equal to 5.12 10 to the power 5 pascals. 5.12 10 to the power 5 pascals. Is that what you get? Don't lose the concentration. Antimega. What that? Everybody okay with that? Yeah. Did you all get those answers? Then you told me that up to this point you get that. But 2 point, no. What? water නේද අපිට ඕනේ 4.8. This should be 4.8 10 to the power 5. Right, okay, wait. 3.2 times 3.2 divided by 4.8. 2.13 10 to the power. Yeah, 2.13. 2.13 10 to the power 5. Is that okay? Yeah, P water. Yes. 4.8. Right. If the above reaction is repeated in a similar manner, but in the absence of nitrogen, deduce the partial pressure of steam, partial pressure of carbon monoxide, partial pressure of hydrogen, and the total pressure inside the vessel. Now, partial pressures don't change now because it's like an inert gas. It is not participating in the reaction. So partial pressures don't change. Partial pressure of carbon monoxide and partial pressure of hydrogen are both the same. Same and the value that you observed earlier, 3.2 10 to the power 5 pascals. Partial pressure of water is just the same, 4.8 10 to the power 5 pascals. It's the opposite of the earlier question. What is the total pressure? Total pressure, add them together. 3.2, 3.2 plus 4.8. 3.2 plus 3.2 plus 4.8. 11.2 10 to the power 5. What do you say? Is that okay, or in the absence of nitrogen? Right? Okay. Right. So then the next one is on the other side, it says suggest one possible industrial use for the sign gas. What is the possible industrial use for the sign gas? You have carbon monoxide and hydrogen. You know, under blast furnace, we understood that carbon monoxide and oxygen giving you carbon dioxide, it's an exothermic reaction. Exothermic. So energy is released. Hydrogen can also be burned with oxygen to give you water. So at the end, there is also exothermic. So this is a mixture where you can burn and get more energy. So this can be used in industry to get energy, to obtain energy and used as a fuel. Yeah, blast furnace, iron industry. හරි නේද? එහෙනම් so that is done. අපි බලමු next week we'll look at 63. ඔක්කොම try කරන්න. 63 if you haven't done it already. 63 ඉඳලා අපි 65 වගේ වෙනකම් කරමු. Like at least that entire page. Right? ඊට පස්සේ we will do මම තව සති 3ක් විතර කරන්නම්. I don't know whether you have exams like next time and then you won't be able to participate. Right? Didn't you say when the inert gas is present, it affects the molar ratio? So it affects the partial pressures too. Can you please, didn't you say when an inert gas is present, I didn't say that. I said that whenever inert gas is present, molar fractions are changed. Total pressure also changes so that it doesn't affect the partial pressure. It doesn't affect the partial pressure. Right? Okay. So it doesn't affect when you have inert gas. Like nothing happens. Whether you have inert gas, whether you don't have inert gas, their partial pressures don't affect. The partial pressures are not affected. Correct? I have done a small calculation also in the note. I specifically I have given that. Doing a small calculation with A, B, C, D and adding alpha, some inert gas. It was say we will look at the ester tutorial also, very last part, and we'll finish it off. එතකොට අපිට තියෙන්නේ ආය nitrogen containing compounds, right? So we'll finish that also today, just now, right? So esters continued. You remember where I stopped? Esters. I have marked XIV. එතන තමයි මම mark කළේ. Page number 5, XIV. Shall I start from there? Well, CH3, C double bond O, CH3. It gives you CH3, CCl, CH3, C double bond O, CH3, CH3H. Right. So what are we doing? We are going to form an ester. This is the one. So you get CH3, CCl, CH3, and you need C double OH. On the other side, you have a CH3, CH3, H, OH. And add them together, this will give you that. So how are we going to work that out? So you add sodium cyanide and sulfuric. What will happen? Nucleophilic addition reaction take place and it gives you CH3, COH. And on this side you get CN and you get CH3. Right? Then what we do is we react this with H plus H2O. When you add H plus H2O, you get CH3, COH. And this is CH3 as well. And you get C double OH. Now react this with PCl5. PCl5. What will happen? You get CH3, CCl. And this becomes COCl. And this is your CH3. Right. Now I am not going to use this one, right? I will erase this one because you have acid chloride. That is better. And then what you do is you add this. This part will react. Acid chloride will react and it gives you the, what is this? The ester. So that is XIV. I hope you are okay with that. And benzene. Right. Next one, benzene. CH3. This one is CH2. This one C double bond O. CH. CH3. CH3. So we want to convert it to that. So again, we analyze it and see. This is where the ester, right? So meaning you need to have a compound like this. Benzene, you have a CH3 and you get C double bond CH2 and this one is COOH and you can react this with the alcohol. That is how you actually analyze it. Then it becomes easier, right? Now you can see this is auto product. So you attach the CH3 first. CH3 first. Then there's a carbon with COOH, all these bulky groups. So you do the Friedel-Crafts acylation. Let's attach the CH3 here. And here C double bond O CH3. Friedel-Crafts acylation. Now we can attach sodium cyanide. CH3, COH, and then CN. And this is the CH3. Add sulfuric. When you add sulfuric, you get double bond, right? CH3, C double bond CH2, CN. Let's convert it to that. So I will write down the reagents, anhydrous AlCl3. Okay, ne? Shape. And Hertz. Right. What is the next step? Ken Balan, how do you do the next step? Can't we reduce esters? Bad. Reduce esters, reduce current by sodium borohydride. Lithium aluminum hydride is the only way to reduce. Right? CH3. CH3 next one. What is the next one? Can CH3, COCl, anhydrous AlCl3. What is the next step? Sodium cyanide attack. Sodium cyanide and then sulfuric. Then add the concentrated sulfuric. Heat. Okay, you can remove a water molecule. Now add H plus H2O. Then add the alcohol and sulfuric acid. So that is done. This is also done. Clear? Everybody got that? Right. Aniket Balan. XVI. Right. Questions? Any questions? Will the double bond break when adding water? Like, no, it depends on the conditions that you use, right? For hydrolysis, you use a certain condition, you are not heating. If you want to break the double bond, you have to heat it. Then only, water molecules will add across the double bond. Just by adding, it won't work. Because anyway, alkenes, they are not very soluble also, no? Right? Such a compound is not very soluble as well, right? So it depends on the condition as well, right? So CH3, CH2, C double bond O, CH3. And then we want to convert this into CH3, CH2, C double bond O, CH, CH3, CH3. Now, first thing is you need to add, now if you're going to break this, the easiest way to break this is you can use lithium aluminum hydride. But here you don't need that kind of condition. Dilute sodium hydroxide heat. That's the first step. And the second step, don't forget, you need to add H plus H2O. Then only you get the carboxylic acid. So you get CH3, CH2, COOH. Right? Carboxylic acid. Okay, let me answer that question after doing this. PCl5, CH3, CH2, COCl, and then from here to there, you add CH3, CH, CH3, and this is OH. Again, to convert CN to COOH is water necessary. CN to COOH, it's hydrolysis. Your water is important. That CN, it turns into COOH because of water. That oxygen comes from water. So water is important. Is there any chance that the concentrated sulfuric CN turns into COOH? No. Concentrated sulfuric is different. It's concentrated. Here you use dilute because water is the one that you actually add, right? Not concentrated sulfuric. Sulfuric is used to dehydration. There is no water there, right? Uh, so dilute sulfuric, there's no chance. They are independent. They are going to work independent. Is it clear? Right. Anikat බලන්න. The X VII. Okay, right, fine, no problem. Right. So what is the next one? It says CH3, C double bond oxygen, CH2, CH2OH. CH3, CH2, CH, CH3, O, C double bond O, CH2, CH2, CH3. Right, okay. So how are we going to do this? The first thing that we do is we'll add the sulfuric, concentrated sulfuric. 170 degrees, you get this compound, CH3, C double bond O, CH double bond CH2. Now what you do is you add the hydrogen platinum. CH3, C double bond O, CH2, CH3. What is the next one? Now you need to convert it to an alcohol. So how do you look at that? Sodium borohydride, that's the best method. Sodium borohydride, make sure you don't forget methanol. You get CH3, COH, H. And then you have CH2, CH3. Now you have the oxygen at the right place, right? Now you add the acid chloride on this part. CH3, CH2, CH2, CO, Cl. Right. Go to the next page also. Now only the last page. Last page. Let's look at that. But energetically I know you guys are very tired. Then me mansila ne. But then right? Then do it. Don't worry. C double bond O, O, CH, CH3, CH3. And you get CH3, C double bond CH2, CH3. Right? So how can we do that? Let's add sodium hydroxide methamphetamine. Sodium hydroxide, NaOH. Heat. Now, alcohols don't react with sodium hydroxide, so therefore there's no problem here. OH, CH3, and H, isn't it? What is the next step? Now let us add acidic potassium permanganate, H plus KMnO4. You get CH3, C double bond O, CH3. Now add the Grignard reagent. CH3 MgBr, anhydrous ether, H2O. What is the next step? Concentrated sulfuric. 170 degrees. So it will remove a double bond and it gives you that. Right, okay. Last question. Benzene, C double bond O, CH2, CH3. It's ester. Now what you do is you need to get CH2 N, and on this side CH3, on this side also CH3. So it's a tertiary amine, right? This is the way to do it. You remember whether you can do this. You break that bond. How do you break the bond? By adding sodium hydroxide. Dilute sodium hydroxide. When you add dilute sodium hydroxide heat, you get the carboxylic acid salt. Add the H plus. You get the carboxylic acid. React this with PCl5. You get the acid chloride. Acid chloride, then these amines will react. Yeah. So I am going to add this amine. CH3, NCH3, H, C double bond O, and it gives you the amide. Nitrogen substituted amide. Now what you do? What is the next one? Okay, I'm sure you remember. What is the reaction? Lithium aluminium hydride. Anhydrous ether. H2O. But the reaction, right? How do you convert that lithium aluminum hydride, anhydrous ether, and H2O? Anybody want me to remind that again? Hmm? Right? So this is the last reaction of lithium aluminum hydride. CONH2. So if you add lithium aluminium hydride, what will happen is it removes the oxygen and replaces with CH2 NH2. I think same thing. If you have two nitrogens, it's not there, and let us say you have a CH3, and then if you add lithium aluminum hydride, what will happen? That oxygen will leave and gives you CH2 N CH3 CH3. This is the inspiration. Lithium aluminum hydride, anhydrous ether, H plus H2O is the inspiration. Is it clear? Did you understand that? Right. Okay. Let's find the answers to the remaining ones. Question number 1. Esters can undergo nucleophilic addition reactions. What do you think? Nucleophilic addition reactions, I don't think. Nucleophilic substitution can take place, not additions. Right? So, first one I take it as wrong. You all also tell me. Esters react with dilute acids and give corresponding carboxylic acid and the alcohol as products. In this reaction, both act as a nucleophile and the ester undergoes hydrolysis. I think that is perfectly right. Reactions of esters with aqueous sodium hydroxide will give carboxylic acids as the only product. That is wrong. It doesn't give carboxylic acid. It gives you the salt of the carboxylic acid. And it gives you an alcohol also. In this reaction of esters with Grignard reagent, ester is first converted into a ketone, then it will convert it into a tertiary alcohol. I think that is right. Ketones react faster than esters with Grignard reagents, but it is possible to stop the reaction as at the ketone stage. ketones react faster than the esters with the Grignard reagent. But it is possible to stop the reaction at the ketone stage. CH3, C double bond O, O, CH3. GCl. So this attacks over here, comes back, it gives you this. So it gives you the ketone. CH3, C double bond O, CH3. What do you think? It is possible to stop the reaction at the ketone stage by adding 1 mole. I think it is possible, right? I think right. Esters react with sodium borohydride and reduce to give alcohol. That is wrong. Esters are polar molecules. Fine. Esters cannot form hydrogen bonds with water molecules since the lack of OH groups. But water molecules contain hydrogen and this contains oxygen. So there can be a hydrogen bond that can form. CH3, C double bond O, OCH3. But water contains the hydrogen attached to oxygen. So this is a hydrogen bond. Esters cannot form කියන එක වැරදි. I'll write these letters, otherwise A, B, C, D, E, F, G, H. Esters cannot form hydrogen bonds. No, that is wrong. No. Cannot form hydrogen bonds is wrong. GH. Boiling point of esters are lower than the carboxylic acid with the same number of carbon atoms. HI, yes, that's right, because they have hydrogen bonds. These ones have dipole-dipole interaction. Alkaline hydrolysis of esters is faster than acid hydrolysis. IJ, yes, that's right, because you are reacting OH minus. And in water, acid hydrolysis, water molecules are reacting. Here, this has a greater nucleophilic character. Nucleophilicity is high. So therefore, it's a faster reaction. Hi, now any questions? Then every organic molecule contains hydrogen, so it can form hydrogen bonds. It can't form hydrogen bonds. Because those hydrogens should be directly attached to what? Directly attached to a electronegative atom. So hydrogen should, in order for a hydrogen to form hydrogen bonds, it should be directly attached to an electronegative atom such as oxygen, fluorine, and nitrogen. So every organic molecule can't form. Now methane can't form the hydrogen bonds because hydrogen is attached to this name. Hydrogen is attached to carbon. So that can't form a hydrogen bond. Can? Is it clear? All organic molecules should dissolve. Any other things that you need to say? This one here this is like a hydrogen bond. This is delta plus and this is delta minus. That delta plus is directly attached to a delta minus. So this hydrogen is a hydrogen bond donor, and this is a donor and this is an acceptor. Hydrogen bond donor and hydrogen bond acceptor. So that is therefore it can form a hydrogen bond. That is why that is. Anything else to say? Anything else to question in this part? Now esters are also done, right? You have amides and amines and amides. Next week we'll start with what? Shall we start with the next week? You have exams. The somebody said that they have exams. I remember. But yeah, okay. Right. I'll let you go. Right. No exams. Then we'll do. Right. Okay. Ah, yes. Okay. Right. අපි බලමු මොන හරි කරන්න. I'll do and I'll keep the recording in the මේකයි ඉතින් බලන්න ඕනම් you can do it, but then the answers also I'll send so that anyway you have access to this. හරිද? Right. Okay. හරි පුතා. Good night. Thank you. Right. Okay. Right. Okay. Bye.